Hello again, everybody. Welcome back to MTED 110. Today we're going to be starting Chapter 9. This is Lecture 9A. Let me pull up the slides and we'll begin. All right, so this chapter is all about ratios, rates, proportions, and percents. In particular, the first lecture, 9A, is pretty much all about the first three: ratios, rates, proportions, and percents. Sorry, try to say that 5 times fast, right? Ratios, rates, proportions. Anyway, um, this chapter builds on a lot from the stuff that we learned in chapters 6, 7, and 8. So make sure you're comfortable with those, and this stuff will be a lot easier. All right, let's begin. Actually, this is something we had talked about a while ago, but it may not seem like it at first, but we measure things as ratios. So, for example, I gave an example like this in a previous lecture. What do we mean when we say a box has a volume of 27 cubic centimeters? We mean that 27 of those little cubic centimeters fit inside of that box. And that's a ratio. Whenever you start talking about like how many of those fit inside, you're talking about division at that point. Or for example, what do we mean when we say 1 yard is equal to 3 feet? We mean you can fit 3 feet into 1 yard. So 1 foot is 1/3 of a yard. There you go. There's that ratio. Or yeah, like what about if we say the maximum occupancy of a room is 40 people? We're saying how many of those people you could fit into that room. So in terms of maximum occupancy, one person represents 1/40th of that maximum occupancy, and that's a ratio. Yeah, these are all ratios. So as maybe unintuitive as it sounds, we measure things using ratios. All right, and here's a good example. I like this example because one of my previous 110 students, she said that she wanted to go into like industrial real estate. I think that's what she said, or it was commercial real estate. She wanted to go into commercial real estate, and I was like, oh, this question is right up your alley then, since you're going to be looking at like large swaths of land, right? So here's a question that I want you to think about at home, and then try to see if you can answer it. So the question says this. A new housing subdivision offers rectangular lots of 3 different sizes, and those 3 sizes are listed right here. If you were able to view those lots from above, like if you were in a helicopter flying over and looking down, the question is which one of these 3 would appear the most square? That's the question. Which one would appear nearly square? So think about that. All right, and now talk out loud about what you thought. Remember, you can talk to yourself, you can talk to your dog, your cat, your friends, your children, your parents, whoever you want. Hopefully, your group members. Think about it and talk about it. Okay, and now let's think about it and talk about it together. So there's a couple of ways to approach this. For one, some of you might have noticed that if you take 114 and subtract 25, you'll get some number, and the same thing for this and this, right? So let's look at the results. Sorry, I should say this first. Really, this is asking, how do we measure squareness? How can you really tell something is square or not, right? Um, if you do an additive comparison, you'll get these results. And I decided to go with the large numbers on top. Oops, just so that everything is positive. And you get those. So which one of those is the most square? So you're kind of like, well, I don't know. What does it mean to be the most square? Should it be the smallest of these numbers or the biggest of these numbers? And then when you start looking at the actual values, you're like, and then you look at this one over here and you're like, that one's like almost, it seems like it's almost twice as big, right? But there is the key. If you're thinking about something as being twice as big as something else, you're doing a multiplicative comparison. And that's not what this is. This is an additive comparison. This is additive comparison. So let's look at the multiplicative comparison and check it out. If we take the ratio of all of these different lots, right, then we get these results right here. That's 1.52. This one is about 1.16, and this one is about 1.324. And it turns out that the correct answer is actually the middle one. And the reason is because of this. This ratio is very, very close to 1. So think about that for a moment. What does it mean for the ratio of 2 sides of a rectangle to be really close to 1. Think about that for just a minute. Hmm. Hmm. Well, if the ratio of the lengths of the sides is really close to 1, then that means that the lengths of the sides must be really close to each other, right? Yeah, because if I take the width and the length, for example, and I divide those and I get something that's almost exactly 1, that means they must both be the same length, right? So, and if they're different lengths, then that ratio will deviate from 1. And the more disparate they are, like, if you've got a rectangle that looks like this, then the ratio is going to be very, very far away from 1. Because what is a ratio, right? It's how many times this goes into that. So what I'm thinking of is like, oh, how many times does this go into this length up here? 1, 2, 3, 4, 5, 6, 7, 8. That's definitely not once, right? But if this thing were much, much shorter, if it was more square, for example, then you would only be able to fit 1. And there would be your square. So this is a way that we measure squareness. We measure it by a ratio of the lengths of the sides of the rectangle. All right, here's another one. In some countries, indoor skiing is very popular. So they'll make ski slopes that are built in these really big arenas and they cover it with plastic fiber, and that simulates packed snow. So let's say in one arena, there are 3 slopes. And suppose you have measurements on each of the 3 slopes that tell you the length of the base, the width of the base, and the height of the ski slope. And the question is, how could you decide which of the 3 slopes is the most steep or the least steep? So think about that for a minute. All right, and now talk out loud about what you were thinking. All right, now let's take a look. Let's think about this. We're trying to measure steepness. And so you might kind of wonder like, well, how can you measure steepness exactly? And it's funny because it's very similar to what we were just talking about a moment ago, right? Because steepness is, well, let me give you a picture here, right? Um, if I had a very, very short height, but a very, very long, a very, very long base, then we could say that that's not very steep, right? Like that slope, the slope of this line right here is not very steep. However, if we just flip that picture around, maybe I can actually do that here. If we flip this picture around, let's see, can I? I don't think I can. Maybe? That's all right. I won't bother with that. I'll just do it. I'll just say this right here. If I were to flip it around and do it like this instead, that's a very steep slope. So pretend these lengths are the same right here. Those lengths correspond, and these lengths correspond. Well, in this top situation here, I would say that's not very steep at all. So it's not very steep at all. But over here, I would say that's very, very steep. Imagine skiing down these things, right? It's like your little person here. You're gonna like go skiing down these things. This I could see like surviving, right? This one, I don't know. I don't know if I'd survive that. Anyway, so the interesting thing here is that it's not the lengths of the sides when you compare them additively that gives you that information, right? Because it depends on what order they appear in, and that doesn't make any sense, right? So what we really need to do is we need to measure or we need to think about the ratio of those lengths. So what we really need to do is we really need to think about, oh, how high up is the slope? Like how high does it rise, you might say? And then let's compare that to how far you go left or right. Maybe we can call that the run, right? And does that look familiar to anybody? Rise over run? What do you think? That's the slope. That's the slope. That's what we talk about whenever we talk about slope. Slope of a ski lift, slope of like a wheelchair access ramp, all of those things. The slope is always this concept of rise over run. And that's a ratio. That's a ratio, and that's how we measure steepness. There you go. Pretty cool, huh? I think. All right. So now let's do these. This is a fun section because if anybody is interested in cooking or baking or making things or mixing drinks, this is the mathematics that you need to be able to do that. You need this type of mathematics. And actually, what's cool is over at Long Beach City College, there's a class called Culinary Mathematics where we talk about these things a lot because chefs have to do math all the time. But the math they have to do is much more related to proportions and sizes and measuring things, right? Well, if you want to be a really great chef or even just a good cook, you need to be able to scale recipes up and down. You know what I mean? So let's think about this for a minute. We're going to answer some of these questions and then I'll leave the rest for you to do on your own. Here are four potential juice mixes: mix A, B, C, and D. Let's focus on mix A for a minute here. Or actually, no, sorry. Mix A, B, C, and D. Now, A has 2 cups of concentrate to 3 cups water. And these are great because I want you to actually visualize like a cup, right? Visualize a cup with some concentrate in it and some water added. All right, that's what I want you to have in your mind when you're thinking about this. So mix A was 2 cups concentrate to 3 cups water. Mix B was 1 cup concentrate to 4 cups water. Mix C is 4 cups concentrate to 8 cups water, and mix D is 3 to 5. So which recipe do you think will make the strongest juice? Huh? Which one is going to make the strongest juice? Think about that for a minute. All right, now let's talk about this one together. If it's going to be the strongest juice, then that means that it's not just going to have the most concentrate, it's got to have the most concentrate and also like the least amount of water. Because what I'm imagining is I'm imagining taking like one of those cans of orange juice concentrate and dumping the whole thing in a cup, and then that's it. That would be really, really, really strong. And the more water I add after that, it's going to dilute the concentrate and it's going to make it a weaker juice, right? So really, we have to compare how much concentrate is in the entire mix. That's the thing. So it's a mistake to start comparing this number here to like compare this to this or this to this because those might be even very far apart, but uh, how they relate multiplicatively is what's going to give us the answer. So let's think about this for a second here. Let's look at mix A. 2 cups concentrate to 3 cups water. My question is, what part of the entire mix is concentrate? Think about that. What part of the entire mix is concentrate? Now try to work it out. All right, let's go over this together. This is exactly the same thing that we did in chapter 8, right? With all of the candy bar examples where it was like 4/5 and 1/2, and you had to like do these comparisons, and the referent unit kept changing over and over. The reason that we were talking about that is because now we can use that here. So let's look at this one. I'm going to look at mix A. 2 cups concentrate and 3 cups water. That tells me there's 5 cups altogether. So that means that the ratio of concentrate to the entire mix is 2 to 5, 2/5. And then I'm going to go down and do the same thing. For mix B, the ratio of concentrate to the total mix is 1/5 because there's 5 cups there. For mix C, the ratio of concentrate to total mix is going to be 4/12. We could actually reduce that, right? What is that, 1/3? Yeah. And then the last one, 3 cups of concentrate to 5 cups water, that's going to give us 3/8 concentrate to total mix. And so now we're basically trying to say which one of these numbers is the largest. Because if the largest percent, or sorry, the largest ratio here is the one that's going to be the strongest juice because we're comparing the concentrate to the total mix. So now we have to rely on everything that we learned back in chapter 6 and 7, right? Excuse me. Chapter 6 and 7, because now we're just comparing fractions and we're comparing the size of fractions. So let me ask you, which one of those 4 fractions is the largest? What do you think? Okay, let's try this together. Off the top of my head, I'm pretty sure that it's 3/8, because I know 1/5 is quite small. 1/5 is what is that, 20%? 2/5 is 40%. Oh, wait, I think I was wrong. 2/5 is 40%. 1/3 is about 33%. And 3/8 is 37.5%. So even just like saying it out loud as I represent them as percentages made a lot more sense to me. Let me write that out. 2/5 is 40%. And I'll let you try to calculate that if you'd like. 1/5, 1/5 is 20%, because five of those will fit, 5 20s will fit into 100. And then 1/3 is 33.3 repeating percent. Remember, you got to have that bar because 1/3 is not 33.3. 33.3 is not 1/3. 33.3 is 33 and 3/10. That's not 1/3. Okay, 33 and 3/10%, I should say. And then 3/8, that's 37.5%. So now we can see that the strongest juice is juice A, mix A. That's the strongest. And now we can also see which one is the weakest, right? The weakest one is mix B. Mix B is the weakest because it's only 20% strength. There you go. So that's how you can do that type of stuff. And that's why this type of math is important. And it's important to be comfortable with it, right? Okay, let's do the second one. You want to make juice for 240 people at half a cup per person. How much concentrate and water would you need for mix A, B, C, and D? Let's do mix A together. Let me erase some of this stuff. Oops. There we go. Juice for 240 people at half a cup per person. Okay, so if we need half a cup per person, then we're going to have 120 total cups because we're doing half a cup per person and we have 240 people. So we're going to end up making 120 cups total. All right, and then the question is, how much concentrate and water would we need for mix A, B, C, and D? Well, this is where that multiplicative reasoning comes in and all that stuff from chapter 8 comes in. This is the total of our strip, you could say, and we have to break that strip up according to these ratios, and then that'll tell us exactly how many cups we need, right? So let's see. I think we said that this was, the concentrate was 2/5, right? So 2/5 of mix A is concentrate. So if we take 2/5 and we multiply it by 120, that's going to tell us that 2/5 of this total amount is exactly how many cups we need. So let's see, what is 2/5 of 120? And at this point, there's all sorts of ways you could do it. How would I do it? What is 120? 120 over 5. What is that? 25? No, not quite. Is it 20? No, is it, I don't know. What is it? What is it going to be? 120 divided by 5. Okay, 5 goes into 100 20 times. Oh, 24. There it is. We need another 4. So this is 2 times 24, which is 48. Okay, so we need 48 cups of concentrate. And now the nice thing is that we know that there's 48 cups of concentrate and there's 120 cups total. So the amount of water we need is 120 minus 48. How would we do that? Let's do it in pieces. I can't see it off the top of my head, right? Let's see, 120 minus 48, that's 120. That's 100 minus 28. That's 80 minus 8, that's 72. There you go, 72. So we need, and then this is where I would actually write the sentence, but I'm a little bit out of space here. We need 48 cups of concentrate, and then we need 72 cups of water. There we go. So that's how we can figure it out. So I suggest that you try those ones, right? Try a couple of those. Just take a minute and work those out on your own at home for a minute. All right, now let's do the next one together. Delete. Okay, so question 3 here says, which is juicier, or which is stronger? 100 cups of concentrate and 101 cups of water, or 2 cups of concentrate and 3 cups of water? See, this is a good problem because remember, it's not so much how big these things are individually that matters. What matters is their ratio. So one thing I see here is if we have 100 cups of concentrate and 101 cups of water, and we were to mix those all into a big pitcher, well, then we're going to have we're going to have 201 cups of fluid, 201 cups of juice, right? But the ratio is essentially 50-50, right? It's like a it's like a 1-to-1 ratio, 100 cups concentrate and about 100 cups water. So the strength of that juice is like 50% concentrate, approximately, right? But if you look at the next one, it's 2 cups concentrate and 3 cups water. So now the concentrate is 2/5, and remember 2/5 is 40%. So here, this is the juicier mix. So that's the juicier mix. And what you can do is you can play around with these numbers so that they seem wildly large, but it might actually switch the result. I'll leave it to you to come up with an example like that. I know you'll see some on the homework, but okay. How much water and how much concentrate? Oh, let's go to question 4 now. Sorry. How much water and how much concentrate are needed to make 1 cup of juice using mix A? Hmm. Hmm. Well, the idea here is that it might be confusing because our ratios are given to us in terms of cups up here. But remember, a ratio is just a scaling factor, essentially, right? It's a ratio of 2 numbers. So really, we're thinking about this. And if we need to know how much water and concentrate we need to make 1 cup of juice, what we know is that 2/5 of the cup is concentrate, and 3/5 of the cup is water. And there it is. So that's how we do it. So even though the unit is suddenly smaller, or I shouldn't say smaller, but we're trying to make 1 of this thing, that doesn't change how we would actually go about the problem, which is kind of cool. All right. I guess I had all that space over there. I could have used it. Okay, so this is one thing you have to watch out with your students. So this question, which is juicier, mix A or mix B, 2 cups concentrate, 3 cups water, 1 cup concentrate, 4. The incorrect reasoning is this, and you'll hear students say this a lot. Mix A must be juicier because it has more concentrate. But remember, that's not really what it is. It's not so much the lengths itself, it's not so much the amounts themselves when looked at individually, it's their ratio, right? It's how they compare multiplicatively. Yeah, exactly. See, that's an additive comparison. But a multiplicative comparison is the more edifying one here. This is the multiplicative comparison lets us actually answer the question. Yeah, we want to compare how many more times water there is, or how many times more water there is than concentrate. That's what we want to know. Because if you keep adding more and more water, it's going to get weaker and weaker and weaker. And if you keep adding more concentrate, it's going to get stronger and stronger and stronger. So what we need to do is look at the ratio. Okay, so when you're working with your students, these are good ideas. Sometimes you use some extreme examples, and that'll help develop intuition. So which is juicier here, mix A or mix B? Mix A is 1 tablespoon of concentrate and a drop of water. Let's see, how juicy is that gonna, how strong is that gonna be? Uh, I think that's going to taste pretty strong. It's basically all concentrate and a tiny bit of water, and the concentrated, there's just so much more of it, it's going to overwhelm the water. Or this, 50 gallons of concentrate, 50 gallons of water. Again, that's a ton of juice, right? That's 100 gallons of juice, but it's about the ratio. It's all about the ratio, not the exact amount individually, right? So mix A is going to be way juicier than mix B, even though mix B is a larger quantity, you could say. That's the idea. It's a larger amount total, but that's not what matters, right? Okay. So Common Core standards, proportional reasoning becomes a big topic in 6th grade when students enter middle school. And this is the key thing here, right? It is built upon multiplicative reasoning developed in the elementary grades. So if students don't develop this intuition in the elementary grades, they start to struggle with proportional reasoning. And then that just leads to more and more things down the line that are harder for them to understand. So we got to catch them early and make sure that they have the tools and the skills to make sense of these problems, not just algorithms, right? Not just algorithms. Okay, so here's an example. This is the 6th grade SBAC, Smarter Balanced exam. And the question says, an artist is using red, blue, and green tiles to create a mosaic. The ratio of red tiles to total tiles needs to be 2 to 5. And for every 2 blue tiles, there should be 1 green tile. So what that's saying is that the ratio of blue tiles to green tiles is 2 to 1. And then the question says to drag these little blocks into the space in such a way that both of those ratios are respected in that mosaic that you construct. And there's lots of ways to do it. There's technically infinitely many ways to answer it. But the way that I would do it is, let's just start. Okay, red tiles to total tiles should be 2 to 5. I'm just going to put 2 red tiles. Why not? And I'll use my red marker here, or my red pencil. Okay, now it says that the ratio of red tiles to total tiles should be 2 to 5. So I need to somehow get 3 more tiles in there, and I can't add any more reds. I can add blues and greens, but I'm going to have to add 3 of those, right? And is that going to let us obey the ratio between the blues and the greens? I don't know. Let's check. For every 2 blue tiles, you need 1 green tile. Oh, how nice. That's pretty handy, right? I can just draw 2 blue tiles and 1 green tile. There we go. And now all of those ratios are respected. The ratio of red to the total, right? The ratio of red to the total is 2 to 5. The ratio of blue to green is 2 to 1. So it's respected. Notice also that this looks very, very similar to the strip diagrams that we've been doing in chapter 8 and that you'll do all this chapter 2. Exactly, because that's a tool that these students use and we want to make sure that they understand how to use it. All right, how about this one? This is grade 7. Tim makes 80 gallons of paint by mixing 48 gallons, by mixing 48 gallons of green with 32 gallons of blue paint. What part of every gallon is from green paint? And then it actually says here, this last part, that this model represents 1 gallon of mixed paint, and the students are supposed to select the bars. They're supposed to select the bars to indicate how much of this total gallon is green paint. Okay, so let's do this one together. Okay, let's see. So we know here that the total amount of paint is 80 gallons. And we know that 48 of those 80 gallons are green paint. So the ratio of green to the total amount is 48 to 80, right? 48 to 80. All right, see now the issue here is that these are all given to us in decimal form. So we need to be able to convert from fractions to decimals comfortably if we want to be able to answer that question. And that's why we talked about that in the previous content, right? The previous chapters and stuff. That's why we wanted to be able to convert back and forth between fractions and decimals. Well, I actually see something quite nice here. Remember, I think in, which lecture was it? Lecture 7? I think it was 7B, possibly. But it said that you'll have was it 7B? I can't remember. Anyway, the idea was that if you could get a power of 10 in the denominator, then it was really, really easy to write the decimal representation. Do you remember that? If not, you should go and think about it some more. But if we can get a power of 10 in the denominator, then we can easily convert this to a decimal. And I see a very nice relationship between the factors of 48 and the factors of 80, mainly that they both have a factor of 8. Let me rewrite this like so. This is 6 times 8 over 10 times 8, right? What is 80? 80 is 10 times 8, and 48 is 6 times 8. And now that we've explored cancellation and what that really means, we know that we can cancel these, and we're going to get the answer 6/10. Well, what is 6/10? 6/10 is the same thing as 60 hundredths, or 60% if you would like. But that's just the same as 0.6. Actually, I didn't even need to do this part, right? I don't need that part. 6/10 is the same as, I'm sorry, yeah, 6/10 is the same as this. 6/10, going all the way back to chapter 2 now. So we just have to shade 6/10. Let's go ahead and do that. And that's going to be green paint. So I'll pick green. All right, right up to there. Right, there we go. All right. There we go. And that's what we expect the student to be able to do, to realize that that's going to be 6/10 and to shade that in. Notice also that's grade 7. So we're expecting students to be able to do this by the time they complete grade 7, or right as they're about to leave grade 7, I should say. Okay. Now we have to talk about comparing ratios at the same title. Yeah, comparing ratios. So now we're going to get a couple very important definitions, and these are ones that you do need to memorize because we're going to be referring to them, and you're going to have to demonstrate your ability to use them. I'll say it like that. So first, a proportion. A proportion is a statement that two ratios are equal to one another. And what we say is that the quantities are proportional. So let me give you some examples here. This is what a proportion looks like. 2/3 equals 4/6. That's a proportion. Or maybe 3/10 equals x over 5 over 5. That's a proportion. So the key thing here is that a proportion has an equal sign in it. Okay, it has an equal sign in it. And it's saying that two ratios are the same. That's what it's saying. So a proportion just says two ratios are the same, except they might be multiples of one another, right? They might be some scalar multiple of one another. In fact, that's exactly what it is. Proportionality means that you're a scalar multiple of another thing. And I think it's, oh, what grade is it? I can't remember what grade it is. I think it's in high school, but at one point, students start talking about um, what is it? Direct proportionality and inverse proportionality, and so on and so on. They need to have this ability to understand that concept. So that's what a proportion is. Okay. Um, Turn that fan on there. Uh, oh yeah, okay. So mix A in the juice examples had a ratio of 2:3 concentrate to water, and we used cups. Now, for any other amount of juice of the same strength, right, of the same strength, like if we wanted to scale up the recipe or scale it down, then there's going to be some number n where we're going to multiply 2 and 3 by that number, and the ratio will remain the same. We're just creating a proportion at that point, right? And students tend to get thrown off by this at first, but remember, this symbol just means 2/3. And what we're saying here is that 2/3 is equal to 2n over 3n, which makes sense, right? Because we know about cancellation, and we know that if you cancel those, you're going to get the same result. And n is basically how many times we want to scale the recipe. It's the factor by which we want to scale the recipe. So if you need to double the recipe, n would be 2. If you wanted to quadruple the recipe, n would be 4. If you wanted to halve the recipe, n would be a half. If you wanted to only make 1/10 of a recipe, n would be 1/10. And that's the idea. And that's why it's true, right? So this is a proportion. This is what a proportion is, saying that those two things are the same. All right, yeah, there you go. We can think of it as n repetitions of the recipe. There you go. Double the recipe, n equals 2, and we have 2/3 is equal to 4/6, which I just showed. All right. Oh, there you go. I guess I got ahead of myself. The proportion can also be written as 2/3 equals 4/6, so all that exploration of equivalent fractions comes into play. All right. Okay, so here's a good question. A picture of each of two juices are made, one with a ratio of 1:3, concentrate to water, and another with a ratio of 3:7, concentrate to water. Which is juicier? And we can rely on all of our knowledge about fractions that we learned previously to answer this. Let's see. Notice that 1 to 3 is the same as 3 to 9, right? 1 to 3 is the same as 3 to 9. Now, 3 to 9 is 3/9, and 3 to 7 is 3/7. So which is bigger? Which is bigger, 3/9 or 3/7? Well, because we went through chapters 6 and 7, we can all tell pretty quickly that 3/7 has got to be bigger because the pieces the whole is cut into a smaller number of pieces. And so if we take 3 of them, we're going to get bigger pieces, right? So 3/7 is bigger than 3/9. And that means that that's the juicier one. There we go, which is larger. 3/7 is larger than 3/9. So the second juice is juicier. And that's the idea. But do you see how all of that stuff from previous comes back in very, very important ways right when these students are entering middle school, like fifth grade, sixth grade, seventh grade, like all of that stuff from the previous grades just comes back in really important ways. Yeah, so in this case, we used our understanding of fractions to compare ratios, and we use proportions. And we use proportions. That's robustness. That's robustness right there. All right, here's the other definition that you will need to memorize. A unit ratio. A unit ratio is a ratio for which the first quantity is represented by some non-zero number and the second quantity is represented by 1. Let me give you an example. This is a unit, or sorry, lost myself, hold on. The second quantity is represented by 1. Oh yeah, this right here. That is what we call a unit ratio. And the reason that we call it a unit ratio is because we're comparing, how do I put it? We're comparing a fraction to a unit. So the nice thing about this particular structure is we're saying that 1 to 3, the ratio 1 to 3, it's the same as 1/3 to 1. So if you wanted to have like 1 cup to 3 cups, it's the same thing as having 1/3 of a cup to 1 cup. And I'm actually excited because I think at the very, very end of this chapter, like the end of the next lecture, there is an actual proportion ratio problem that I had to solve myself, that I'll tell you about. I'm excited. It's very relevant too because I had to mix bleach and water. So you're gonna have to do that a lot right now, right, with COVID-19 everywhere. So it'd be good to know how much bleach you need to mix into water so that your bleach spray is actually effective at killing the virus. But let me go through this funky looking algebra. And I find that this algebra is almost too complex, way more complex than it needs to be. But let's go through it. Now, we know that this is true just by definition. 1/3 is the same as saying 1 to 3. But we can also write 1/3 as 1/3 over 1, right? That doesn't change anything. That's just like multiplying by 1 over 1. But then this, by definition, is 1/3 to 1. So what we're saying is that 1 to 3 is the same as 1/3 to 1. All right, that's the idea. Um, you can get about that by kind of abusing the notation a bit if you think about like dividing both sides, but there aren't really both sides here, so that's why I don't like doing that. Maybe I can explain that some more in the collaboration meeting. All right, but that's what a unit ratio is. Oh, the last thing I want to say about a unit ratio or this definition is that uh, in practice, when we use them, it doesn't, I don't want to say it doesn't matter. Um, we want the 1 to be on the side that we care about. And I'll explain that in the next examples. But what I mean is that a unit ratio is something that looks like this, but oftentimes we will want the 1 to be on the left instead. Because the whole point is that we can basically compare one quantity to the unit. That's what we're really trying to do. Okay, what am I doing here? Oh yeah, so we're gonna do this. Look at this question here. How many cups of concentrate should be mixed with 12 cups of water if we want to make the strength of the juice the same as when we used 3 cups of concentrate and 7 cups of water? Okay, so let's ponder that for just a second here. Okay, we've already got 12 cups of water, and we want to make the strength of the juice the same as when it was 3 to 7. Now you can probably see how a proportion is kind of cropping up, right? But what we're going to see is that we don't have to use a proportion all the time. So how are we going to do this? Okay, this is sometimes referred to as a missing value problem because this is a precursor to solving for x, right? That's really what it is. There are many ways to solve these problems, and the methods vary not only by efficiency, but also whether the procedure makes sense. And now we're going to look at 3 different ways of solving this problem. Okay, solution 1 is using a unit ratio. So think about this. 3 cups of concentrate for 7 cups of water means that for 3/7 of a cup of concentrate, we use 1 cup of water. That's the unit ratio. That's the unit ratio. That's exactly what we're saying. Let me show you how this works. 3 to 7 is the same as 3/7 to 1. There it is. So you can kind of cheat and just do some symbol manipulation if you divide both of these by 7, so to speak. I'm going to write this in red because this is the way that I'm writing this down is not mathematically valid. And in fact, I encourage you to verify that you're allowed to do this, right? Verify that you're allowed to do this because what I'm doing is written in a very misleading way. But if I do this, or sorry, then I'm going to get 3/7 to 1. And that means that I know that I need 3/7, what is it? Yeah, 3/7 of a cup of concentrate to 1 cup of water. So this is our unit ratio. Now that we know the unit ratio, we can just multiply it by the number of cups we need. That's what's so awesome about these things, right? So for 12 cups of water, we're going to need 3/7 of a cup of concentrate for each. So all we really need to do is multiply 12 times 3/7, and the answer comes right out. 36/7, or 5 1/7 of a cup of concentrate. There it is. So that's a unit ratio, and you'll get to practice that a lot too, actually. Um, Here's the second solution. So we can set up a proportion equation. And a proportion equation looks like this. Remember, a proportion has to have this has to have this equal sign. And what we're saying is one ratio is equal to another ratio. That's a proportion. And the question we're trying to answer is this. We're trying to solve for x here. How much of that do we need? So there's a couple ways to do it. You can scale the relationship in a meaningful way by finding a common denominator. Find a common denominator, and then you can compare the numerators. Oop. There you go. And that'll give us the answer. So this shows that the ratios will be equal when 3 times 12 equals 7x, or in other words, x equals 36/7, right? And then I think the last one, yeah, the last way is cross multiplying. We can cross multiply to solve for x, right? We do this thing again, we go boom, boom, cross multiply, and then we get the same solution. Now, I'm pretty sure most of you, or I shouldn't say most, I'm pretty sure some of you remember this type of problem and solving it in this way very intimately, but I encourage you not to default to that way of solving, and I'll show you why in just a minute here. This is a very nice procedure. It's very algorithmic. I would happily program a computer to do this, and a computer would be like, thank you, I would love to do that for you. I'm a computer. But we're not computers, we're human beings. And I don't know about you, but cross multiplication as an algebraic process is not something that just like I intuitively get when I do it, right? No, I lose all intuition and I just play around with symbols, and we're trying to avoid that, right? And there's a reason why, this this is the reason. Studies have actually shown that students often prefer the unit ratio method if even if they've been shown or told that cross multiplication is the correct way of doing that. Yeah, so that's an interesting thing here. Students don't really like cross multiplication when they first learn it because it doesn't make any sense. It doesn't make any sense. There's no intuition. What they prefer to do is solving using a unit ratio. Let's go back and take a look at that one more time. Yeah, come back to this. Let me erase some of these things down here. Okay, so the idea with the unit ratio is that it tells you how much of one thing you need per one of the other thing. Or I should say, it's how much of something you need per one of the other thing. And that's great because if you know what the value is per one, then you can just multiply by how many of those ones you've got, right? Just multiply by how many of those ones you've got, and then that'll tell you your answer. So it's much more natural to do it that way. It's very intuitive. It makes total sense. Mathematically, it's valid, but for these things, this type of thing, oops, this type of thing, it's tough. It's tough for students to make sense of that. Might be surprised. Okay. All right. So another definition, a rate is just a ratio of quantities that change without changing the value of the ratio itself. So in particular, these types of things are rates. 50 meters per second, 35 miles per hour. Those are rates. So the ratio changes, or sorry, what does it say? A rate is a ratio of quantities that, yeah, the quantities change, but the ratio doesn't change. So the numerator and the numerator and the denominator might change, but that actual ratio remains fixed. That's what a rate is. Okay, and that's it. All right, so let's play. Let's take a look at activity 9A, and you're going to be doing stuff very similar to what we just talked about. Oops, that's the wrong one. We'll come to that in the next lecture. Here we go. Yeah, so you're basically just looking for ratios. What's the ratio of vowels to all letters in a document? 2/7 of these letters are vowels. What's the ratio of consonants to vowels? This is a really important one. This is the good cooking example, and you have to solve these problems by using a unit ratio and a proportion. Okay, so I just want to emphasize that you cannot just use only a proportion to solve these. You do need to use a unit ratio to solve a couple of these. All right. And then same with this one. So this one here is another comparison problem. And number 5 is interesting because there's a combination of multiplicative and additive comparisons going on, and you have to kind of keep track of both. So this is why we come to the collaboration meetings, right? Because I can help you work through these. That's the idea. And there's a couple more of those. All right. And so that's it. That's it for lecture 9A. We're going to come back and do 9B. And then I guess, yeah, I guess that's it. All right, have a good one, and I will see you all next time.